In nature, proteins rarely function in isolation. They strongly favor symmetric oligomeric assemblies, snapping together into identical subunits before locking into a rigid three-dimensional lattice. Nearly half of all structures in the protein databank are dimers or higher-order oligomers. Biologically, this is common. Crystallographically, this redundancy provides a massive mathematical advantage. This distribution plots the Matthews coefficient against the expected number of molecules in the asymmetric unit. By factoring in the 1.6 angstrom resolution limit, we can calculate the exact probability of whether the unit cell contains 2 or 3 copies, long before we solve the structure. Knowing the number of copies allows us to average the maps. By superimposing the independent molecular copies onto each other, consistent structural features align, while random background noise cancels out. The resulting signal-to-noise ratio improves proportionally to the square root of n, where n is the number of copies in the asymmetric unit. For highly symmetric assemblies, like viral capsids, this signal multiplier is potent enough to bypass the traditional phase problem entirely. The only requirement is determining the exact spatial transformation needed to align the unphased copies. Look at these Fab fragment domains. The repeating macroscopic lattice is governed by global crystallographic symmetry, but the specific internal relationships between the multiple copies within the asymmetric unit are strictly local. We refer to this local geometry as non-crystallographic symmetry, or NCS. To exploit NCS for map averaging, we must formally define the mathematical operator that maps one local copy onto another. In Cartesian space, this is the transformation operator W of RT. Any general transformation mapping one object to another can be deconstructed into 2 absolute components. The first molecule is rotated around its physical center of mass, defined by matrix R. It is then subsequently translated to its new position, defined by vector T. The true bottleneck of crystallography lies here. We need to determine a precise spatial transformation matrix to average the maps, but we need it before we possess an atomic model, and before we have the electron density phases necessary to visualize the molecules. We solve this by abstracting the physical protein into pure geometry. According to Euler's rotation theorem, any rotation in Cartesian space is defined by a single Euler axis, E, and a principal rotation angle kappa. The CCP4 suite uses the ZYZ Euler convention to define orientation. We map the final three-dimensional position through 3 sequential rotations around specific fixed axes, first by gamma around Z, then beta around Y, and finally alpha around Z. The combined product of these sequential operations forms a 3x3 real square matrix called the direction cosine matrix. Its elements contain the trigonometric sums of the rotation. Extracting the geometry from this matrix is straightforward. The sum of the diagonal trace calculates the principal angle kappa, while the eigenvector belonging to the real eigenvalue E real defines the orientation of the Euler axis E. Calculating this directly requires a structural model. Without one, we relied on the specific geometric signatures these operations leave behind, directly within the raw, unphased intensity data. The most direct geometric signature occurs when rotation is negligible. The rotation matrix approaches the identity operator, meaning the spatial relationship between the copies is driven almost entirely by the translation vector, T. In this triclinic calmodulin structure, the asymmetric unit contains 2 molecules. Between the C-terminal lobes, rotation is functionally 0. Instead, the molecules are shifted along vector A over 2, sitting nearly perfectly parallel to the cell edge. This chart maps a cross-section of reciprocal space, showing the first fingerprint of pure translation. When translation vectors approach integer fractions of the unit cell, they cause destructive X-ray interference. The fractional shift generates systematically weak alternating layers directly along the H-axis. The native Patterson map shows the second fingerprint. Because every single atom in the molecular copy is shifted by the exact same distance vector, the superimposed collinear vectors aggregate. This forms a massive superpeak located precisely at the translation distance. When pure translation dictates the symmetry, the unphased Patterson space isolates the exact translation vector, completely bypassing the need for initial phase data. The next signature involves proper non-crystallographic symmetry, exact point group rotations, like 2-fold or 3-fold axes. In certain lattices, these local rotations run perfectly parallel to the global crystallographic axes. Standard Patterson self-rotation functions map the orientation of molecules against themselves. When a local axis aligns physically with a global crystallographic axis, the massive signal generated by the crystal symmetry sits precisely on top of the local peak, completely obscuring it. But because all the individual inter-subunit vectors project collinearly straight down the unique axis, they generate a distinct signature elsewhere, a highly localized peak in a specific two-dimensional slice of the native Patterson map, known as the Harker section. This map shows the Harker section for a monoclinic fab fragment. The strong peak in the upper right represents collinear vectors of a hidden local axis parallel to the crystal screw axis. We map this peak back to physical space by extracting its geometry. The Harker vector is defined as 2x, 1/2, 2z. Dividing the u and w coordinates by 2 isolates the exact x and z coordinates of the rotation axis. By isolating this specific Harker peak, we bypass the global interference and extract the precise spatial location of a local rotation axis that standard phasing tools are blind to. The final signature involves arbitrary proper rotations. These are local point group rotations that exist in completely arbitrary orientations, possessing no geometric alignment with the crystallographic lattice. Free from the overlap of global lattice symmetry, arbitrary rotations shine brightly in Patterson self-rotation maps. These maps plot the rotation angle kappa directly against spherical coordinates. We map these spherical coordinates onto a 2D plane using a stereographic projection. The rotation axis orientation is defined by an azimuthal angle for horizontal rotation and a lateral angle for vertical rotation. By probing different kappa sections, we deconstruct a complex multimer. At kappa equals 72 degrees, a single massive peak reveals a 5-fold rotational axis. Shifting to kappa equals 180 degrees uncovers 5 peripheral peaks, proving 5 perpendicular 2-fold dyads exist. Using stereographic projections, the internal rotational geometry of a complex macromolecular assembly can be mathematically verified before calculating a single piece of electron density. When we deduce the rotation matrix and translation vector from unphased data, we obtain the Cartesian operator W of r, t. But this operator exists in absolute, real-world coordinates. To correctly apply this transformation to the crystal lattice, we multiply the Cartesian operator by the deorthogonalization matrix. This operation converts the absolute coordinates into fractional crystallographic coordinates that match the skewed parameters of the unit cell. Look at this structure in a trigonal cell. Deorthogonalizing the operator tests if the local rotation axis aligns mathematically with the fractional lattice. Shifting the origin locks this symmetry into the cell's face. It's a true crystallographic axis, redefining the entire space group. The geometry of a biological molecule leaves a strict mathematical imprint on its crystal. By decoding the signatures hidden in unphased reciprocal space, we map those structural relationships and uncover the foundational rules holding the lattice together.